Hello everyone. Today we will discuss about the deep learning, the most interesting part of deep learning, that is autoencoders. Now, the success of deep learning came by analyzing complex behavior of data and unfolding their complexities, unfolding their different important features. But when the data is huge, the storage capacity that comes into play, then there is a big problem. The problem is that sometimes when we apply different machine learning algorithms, they used to fail because when we cannot reduce the dimensionality, when we cannot reduce the dimensionality of that particular data set, then it may go for overfitting or sometimes it may be underfitted. Now, autoencoder, they came into play with a very uh, new and very nice kind of architecture. So we will discuss in this session, we will discuss about the overview of autoencoders, and in next session, we will go for their different types of autoencoders and as well as how they work. And then we will do some hands-on, some projects or some different codings we will show in our latter parts. So here we will discuss about why we take autoencoders as a most important part, one of the most important parts of deep learning. So first, I'll show you something regarding this. So first, we will definitely talk about that what are the autoencoders. So here I can see that we used this term self-supervised machine learning models. So obviously deep learning is a set of machine learning. So we can use this term machine learning models, but why we use this term self-supervised? Now self-supervised, that means something is getting input from any unsupervised data, that means unlabeled data, and automatically they will decode into some output which will mimic the input data. That means that decoder, you can see this is the source of this picture. You can see this is the input image. There will be an encoder. After applying this encoder in this input image, something will happen. It is given this is flattened, but basically what happens, dimensionality is reduced. Then decoder takes data from here, and after decoding, it gets a reconstructed image. You see the term, they are very important. Reconstructed image. What is reconstructed image? Why we call it reconstruction? Suppose you were constructing a building. So when you are constructing a building in a totally empty plot, that means your construction is totally new. But suppose you bought some building and you want to renovate it or you want to redesign it. So you demolished some part of the building. That means you reduced the size and then again you started building in a new design, the same building. Or you want to renovate in the same way that the building which will be built that will mimic the previous building. So that is reconstruction. That is not constructing the new building. So when I studied this particular topic, autoencoders, first time, I was really shocked that what is this? I mean, I have small IQ, a very little IQ. So I thought, what is happening? I mean, what's the necessity of this? One image is going inside. Again, the same image is coming outside. So what's the necessity of this? You understand my point? One image is going inside, something is happening. Again, the output is coming almost similar image to this. So what basically happening to this? I don't understand. Then I dive deeper and I understood what is the basic necessity of this. So self-supervised come from this place that when I give some unlabeled data, so that data, from that data, its dimensionality will be reduced, it will be compressed in this place, which is called the bottleneck or the latent space. And this will be the input for the decoder, which will work in the opposite of encoder, and it will construct another image. That is the synthetic image. And that image will mimic the previous image. If their difference will be low, that means loss is small. So this is the basic thing of autoencoders. So this latent space you cannot control. Now you see, there are two parts, what I already told. This is the structure of autoencoder, one encoder, one decoder. What is the work for encoder? It works as the compression unit that compresses the unit data, input data. So compressing the input data means you are basically compressing the dimensionality. And decoder, it decompresses the compressed input by reconstructing this. So you can check that whenever this image of this cat is taken as input, then what is happened? This is input image. Then it goes to the latent space. That means image is compressed. After that, the decoder takes as input, and after decoding, it gives the reconstructed image here. So this reconstructed image and this image, this is the mimic of this image. This is the mimic of this image. This is the mimic of this image. Got it? So all we understood about what is the basic thing of autoencoder. This is clear. Now we come to the architecture. Now, what is the architecture? Architecture means this encoder and decoder, this is the building blocks of autoencoders. Now, how these encoders and decoders are made. So these decoders and these encoders and decoders, they are nothing but some neural networks. For CNN autoencoder, what happens? We take different layers like convolutional layer, max-pool, flattening, all this thing. And this is obviously, we know CNN works better for image data. And for time series analysis or sequential data, we use RNN, recurrent neural network, or LSTM. So these layers will always contain some specific LSTM or specific recurrent neural networks, these encoder decoders. And it is what I have already said that this is suitable for sequential or time series data. Now, when we apply the autoencoder and where we can apply. So obviously we started with the fact that storage capacity, that means the file compression, that means the dimensionality reduction. So when we reduce the dimensionality for input data, then it is easier to find their complex behaviors. And it works very good for images, videos, and audio files. Another case is image denoising. What is denoising? That means basically without human interaction, we can remove noise from the data. That means we can give a cleaner version. It also works, the denoise autoencoder. This is also used for image processing and sometimes for image transformation. That means some gray colored image can be converted into colored image, but in this case, I will prefer StyleGAN for style transferring. And for upsampling, downsampling, that we also got from UNet architecture. So these are the basic applications of autoencoder. So there are different types of autoencoders, like CNN autoencoder. What I already told, all layers will be different: max pooling, mean this downsampling, filters, different layers will be there. Denoising autoencoder, we also talked about this by removing the noise from image or even audio files. Variational autoencoder, this is the very, very important part of autoencoder section. Very important part. We will come to this variational autoencoder in our later videos, and sparse autoencoder. Next, now we discuss about how autoencoder works. So there anything which is related to artificial intelligence or machine learning algorithm, they are basically based on some mathematical and statistical formulations. If we understand the logic behind these algorithms, that means the mathematical logic, then it is easier to understand how the data is passing through that algorithm. So first, we will talk about the encoder transformation. As we know that our architecture works like the input image goes through encoder, it goes to the latent space, then latent if as a compressed data, and from latent space, the decoder takes as the input, and then it goes to the reconstructed image. And finally, we will calculate our losses. So here, the encoder transformation, we have taken the image data that is in a RD, means it is of dimensionality D. That means R space, real space with the dimension D. That means the number of pixels in image. Suppose if I say 28 cross 28, that will be the image. If I consider that 28 cross 28 is the size of the image, in that case, twenty-eight cross 28, that means there will be 784 pixels. So obviously the dimension will be 784. Now we have that image which will pass through the encoder. So obviously this theta e, F encoder is the linear and non-linear transformation, which all we have already uh, covered up this topic in our neural network section, that we remember y is equal to wx plus b. You should remember this one. This is the linear transformation. And when we apply some activation function sigma y, that basically gives us z. If sigma y, this is say sigmoid function, there are hyperbolic tangent function, ReLU function, leaky ReLU function. There are different types of activation functions, nonlinear activation functions. When we use this, then it will be converted into some other values. So basically, this Z is coming through those activation functions, maybe linear or maybe non-linear, which is acted upon X, that means the input image, along with weights and biases. These weights and biases are basically theta. They are the encoder parameters. Now, you can check in the next line what is happening. Z, what we got, the dimension is K, and K is less than D. That means D is the dimension of what? D is the dimension of the image. Suppose this is 784, and we applied some filter over this. Suppose CNN. Just forget this one. Forget ANN. Just take CNN. So when we apply filter, it is quite obvious the dimensionality will be reduced of the feature map, and that will be placed in the lattice space or the bottleneck, whatever we call bottleneck or lattice space. So definitely what will happen that our Z value will be with much lesser dimension. So this way the encoder works, and this value will go to the latent space. Now we talk about the latent space transformation. So in latent space transformation, latent representation, this is the bottleneck near, and it contains the compressed information about X. As you know, we got from sigma of Wx plus B, or F encoder X comma theta E, that is Z, and retains essential features in a smaller dimensional space. This we have talked about several times. Smaller dimensional space. That means the dimensionality is reduced. And that is the principal work for any autoencoder. That is the principal objective, you can say. Now comes decoder transformation. So obviously, decoder is reconstructing, always remember, not generating, reconstructing that information came through the latent space, though it is reduced, but the information came from the latent space, and decoder is just working in the same way, in the same format, but in reverse way, and it is having the parameters theta d. Their weights and biases will be different, and input will be the compressed latent value, that is Z. Now, this is the hyperparameter tuning. So obviously we know that number of layers, number of nodes, they are all hyperparameters. But in encoder decoder, it is a very interesting fact that always if you increase the number of layers, that won't give you the good result. That means if the number of layers, more layers, it can capture complex pattern, but sometimes it also leads to the overfitting. And fewer layers, they may underfit the data, and sometimes it miss important features also. Now, number of nodes, the same thing. Number of nodes actually determines the capacity of each layer to store information. But if you add too many nodes, that increase computational cost. And again, overfitting may happen. And too few nodes, the same thing will happen as few layers, that it may miss very important information. Now, these are the common loss functions, binary cross entropy. For what? For binary or normalized data, we should determine binary cross entropy loss, and mean squared error or root mean squared error for continuous data images. And right loss function is very crucial for your performance, because whenever you will find the matrix should be selected in a very correct manner. That is the most important part. And size of the latent space. That means the compression. Okay. Smaller latent space, it acts as regularization mechanism. It reduces overfitting. That means the data is very compressed and only the main features, the principal components are extracted. Other data are omitted. And if the latent space is very large, it may go for overfitting. Now, this is the generalization versus overfitting. I mean, this well-trained autoencoder that should adapt to input data for meaningful responses and generalize well to unseen data. This is quite obvious, because uh, when it is well trained, then usually it gives well result for any unknown or unseen data. But for overfitting risk, we have to check the mimics training data too closely. That means there will be very small reconstruction loss and fails to perform on new data. So obviously there will be overfitting. They are the common fact of deep learning. So there is nothing new for autoencoders. So this way we have described that how we did this, how we take an overview of this. But most important part is the loss. This loss function, you always remember that the loss function here is the reconstruction loss. Now, one thing, whenever we usually find the loss function for any deep learning algorithm, what we do, we actually take the predicted value minus the actual observation, the squared, and their average of total training samples. In autoencoder, the reconstruction loss is basically generated by the reconstructed data. That means the reconstructed output, that is not the generated output, that is not the predicted output, that is reconstructed output minus the original input and their squared norms, averaged by total number of sample. If this reconstruction loss will be minimized, then we can say that autoencoder has been trained well. So this is the overview of autoencoder. In our next video, we will talk about the different types of autoencoder, how they work, their working principles, and in later version, we will also talk about how we will work on autoencoder in PyTorch as well as in Keras platform. So, okay, goodbye then, and see you in next video.